Welcome to this explainer. Today we're diving straight into a dense but absolutely fascinating new research paper out of Google and NYU. We're going to unpack a revolutionary tool called TurboQuant, and we'll see exactly how it solves one of the most massive hardware problems holding back modern AI right now.
Okay, let's just jump right in. Imagine for a second if we could shrink the memory footprint of a massive large language model by a factor of 5, like completely effortlessly and without losing a single drop of its intelligence or recallability. Sounds impossible, right? Well, that's exactly what we're looking at today.
But to understand how they pull off this magic trick, we first need to get a handle on vector quantization, or VQ. Think of it as the mathematical art of aggressively packing a massive suitcase of data. Specifically, it compresses high-dimensional Euclidean vectors. So it takes these highly precise, multi-layered data coordinates and squishes them down into much smaller, low-bit-width integers. The whole goal here is to make the data physically smaller while minimizing any actual distortion to the underlying geometric structure.
So here's our roadmap for today. We'll cover 1. The AI memory bottleneck. 2. The quantization dilemma. 3. Enter TurboQuant. 4. The two-step magic. 5. The needle in the haystack. And finally, 6. Information theory limits.
Starting off with Section 1, the AI memory bottleneck.
So, you probably know that decoder-based transformer models, which is the architecture behind the biggest LLMs we use today, have to store something called a KV cache. That's the key/value embeddings from all the previously generated tokens. Now, as these models read longer and longer contexts, this short-term memory just explodes in size. We're talking about massive, high-dimensional vectors that create some pretty terrible inference latency. Ultimately, moving all this data back and forth between the system's main high-bandwidth memory and the processor's ultra-fast SRAM cache becomes the ultimate bottleneck. It literally clogs up the system's hardware.
Which brings us to Section 2, the quantization dilemma. When it comes to packing our data suitcase, researchers basically have two choices, and neither is great. Offline quantization methods are highly tailored, sure, but they require heavy pre-processing and data calibration. They're just way too slow for dynamic, real-time AI applications where text is being generated on the fly. On the flip side, online quantization is instant. It's data oblivious, meaning it doesn't even need to study the data first. But here's the catch. Current online methods often distort the data way too much. They introduce bias, and that essentially ruins the accuracy of the inner product estimations, which is the underlying math the AI relies on to connect related concepts and retrieve information.
Section 3. Enter TurboQuant.
TurboQuant completely shatters this dilemma. It's incredibly fast, it works entirely on the fly, and it compresses data perfectly without introducing that math-ruining bias. What makes it so special is that it's highly accelerator-friendly. That means it runs beautifully in parallel on modern GPUs without slowing anything down. And crucially, it delivers unbiased inner product estimators. Simply put, when the AI searches its compressed memory for a fact, it retrieves it perfectly, every single time.
Moving to Section 4, the two-step magic.
So how does the algorithm actually pull this off? Well, the researchers use a really elegant two-step process. First, they take the input vectors and apply a random rotation matrix. Why? Because doing this induces a predictable beta distribution, meaning the data magically organizes itself into a familiar bell curve-like shape. In high dimensions, these coordinates become nearly independent, which lets the algorithm quickly compress them using a continuous k-mean solver, basically grouping similar data points together. Now, that handles the bulk of the compression, but it still leaves a tiny bit of mathematical bias. So for step 2, they apply a quantized Johnson-Lindestraat's, or QJL, transform. It sounds complicated, but it's basically a brilliant one-bit fix applied just to the residual error, and it completely neutralizes any lingering bias.
Just look at the difference in these error distributions. The side-by-side really tells the story here. On the left, we have the TurboQuant production model, our two-step unbiased method. Notice how it's centered perfectly and symmetrically on 0 across different bit widths? It is mathematically pure. Now, look at the right side, which shows just the step 1 MSE method. See how at lower bit widths the data skews off-center? That skew right there is the exact bias that ruins AI recall. By combining both steps, TurboQuant achieves that perfect distribution you see on the left.
Section 5, the needle in the haystack.
Okay, the computer science theory is beautiful, but let's be real, does it actually survive in the wild? We call this the needle in a haystack test, and it's the gold standard for testing whether our aggressive suitcase packing actually ruined the data. We bury one specific sentence inside up to 104,000 words of text, compress the AI's KV cache down to just 25% of its original size, and see if the AI can still find that single hidden needle.
This visual is an absolute mic drop. Notice the recall accuracy across these different document depths and context lengths. Green represents perfect recall. Over on the left is the uncompressed massive Llama 3.18b model running in full precision. It scores a 0.997. Now on the right is the highly compressed TurboQuant model running at just a fraction of the memory footprint. Its score, exactly 0.997. It's wild. We have achieved absolute quality neutrality. The AI quite literally doesn't even realize its memory has been shrunk.
And it doesn't stop at simple retrieval either. When you look at broader generation tasks, things like complex coding completion or multi-document summarization, TurboQuant leaves other popular compression methods completely in the dust. It vastly outperforms previous token-level methods like SnapKV and scalar quantization algorithms like Kivi. And the researchers achieved all of this while compressing the memory by over 4.5 times. It runs at an incredibly efficient 2.5 to 3.5 bits per channel, dynamically allocating just slightly more bits to outlier channels so it can maintain that flawless performance during streaming generation.
Finally, Section 6, Information Theory Limits.
Let's wrap this explainer up by looking at how close this new tool gets to the absolute laws of mathematical physics. According to Claude Shannon's source coding theory, which is a foundational principle from way back in 1959, there is a fundamental mathematical limit to how much we can compress any given data before it's just destroyed. Well, the researchers proved that TurboQuant operates incredibly close to this absolute mathematical ceiling. Across all bit widths, it differs from the theoretical perfect limit by only a tiny constant factor of roughly 2.7. It is quite literally bumping its head against the limits of information theory.
Which leaves us with a pretty provocative thought to end on today. Memory bottlenecks are exactly what limit the context length and the reasoning depth of the AI models we use right now. So, by elegantly solving this communication bottleneck and shrinking an AI's memory footprint by 5x without losing a single drop of intelligence, well, the ceiling for what AI can process and remember tomorrow has just been blown wide open.